Okay, let's review Math 1010. This is lesson 5.1 from Module 5. There are 6 objectives. The first one, find function values for rational functions. Example 1. So we have a function, f of x equals numerator 9x squared minus 8x, denominator 6x. I'm going to set this function up in blanks. So essentially I'm going to put parentheses around all the x's and then rewrite this without any x's, so just the blanks. This is what I do on all functions, all kinds of evaluations, because this allows me to keep the order of operations intact. We plug in -3 into the blanks. And now we simplify. The numerator, we have 9 times 9 minus 8 times -3, that would be plus 24, and the denominator is -18. So that is 9 times 9, 81 plus 24 over -18. We're looking at 105 over -18, which we can simplify and divide by 3 to simplify, and our answer would be -35 divided by 6. All right, let's take a look at the next example. Example 2, another function, find f of 4. So I'm going to set the function up in blanks, exactly as I did before. And when I plug in 4 into the blanks, first thing that I see is the denominator is 0. I don't really care so much about the numerator. 0 in the denominator, undefined. So now there's a lot of possible answers that people use in situations like this that are not always correct. So since the question is find a function value, I can't find it because it's undefined, so what I answer for find f of 4 is does not exist. If you're trying to solve an equation and you get no solution, then you write no solution. You could say the function value, so the function is undefined, but the value does not exist. I hope that makes sense. All right, let's move on. Okay, the second objective, simplify rational expressions by removing a factor equal to 1. So example 1, I'm going to reduce the biggest factors of 1 that I can get. So we have 9 y to the 6th, and there's a 9 in 45, and there's definitely 6 y's in the y to the 12th. So I'm going to write this, the denominator, 45 is 9 times 5. And y to the 12th is y to the 6th times y to the 6th. Now I can remove the equal factors of 1. 9 divided by 9 is 1. Y to the 6th divided by y to the 6th is 1. Now notice there's nothing left over in the numerator. However, I keep saying 9 divided by 9 is 1. 1 is left over when you reduce factors of 1 if nothing else is there. So our final answer is 1 divided by 5 y to the 6th. Look at the next example. Example 2, 7x plus 21 divided by 7x minus 21. We are trying to reduce factors of 1. Now a factor is separated by multiplication. This 7x and this 21 is separated by addition, which means that these are not factors. So there's no factors right now to reduce. These are terms. Terms don't reduce like that. However, we can factor the greatest common factor on the top, 7, giving us x plus 3, and then the bottom, 7, giving us x minus 3. And now we have two separate factors, and one of these factors reduces because 7 divided by 7 is 1, leaving us x plus 3 over x minus 3. Okay. Time for the next objective. simplify rational expressions, and list all restrictions on the domain. These are usually, when talked about domain, functions, which is what we see here, f of x. Okay, so let's first off, again, because of the subtraction, this x squared is a term, no factors. And because of this addition, this 7x and these 14, that's a term, 2 terms in the denominator. So we have to factor first. The numerator is a difference of squares. So the square root of x squared is x, the square root of 4 is 2, and the difference of squares, they are conjugates, so 1 plus, 1 minus. Denominator, we can pull out the 7, leaving us x plus 2. Okay, we can now see x cannot equal negative 2, because negative 2 plus 2 is 0, and dividing by 0 is undefined. Now, we do have a factor of 1, so here we are simplifying the rational expression. Probably would even be better written function. And we have x minus 2 over 7. Now this form, it doesn't look like x can't equal negative 2, but since it's equivalent to the original, where negative 2 causes divide by 0, we have to tell people to avoid that value by specifying the restriction on the domain. That would be the simplified function. Well, the expression, you could write the f of x equals for a more complete answer. Take a look at the next example. Example 2. Okay. Now the first thing I notice is the top one is out of order from the bottom one. Now I like the x first, so I'm going to start off by factoring out a negative 1 on the top. That's going to change this 49 to a minus 49. I'll write that second. Change the minus x squared to an x squared, and I'll write that first. The point of doing this is just to get everything in the same order, which will allow the simplification to be much smoother. All right, so factoring. Difference of squares on top. So we'll have x plus 7 over x minus 7. Denominator. 2 binomials. X and x makes the x squared. 49, 7 and 7, and both minus, so that we can get the minus 14 inner and outer products. And again, here we see a factor of 1. We also see x cannot equal 7. Now, even though we reduced that, it's still obvious. However, they want us to explicitly list these. So, negative x plus 7 over x minus 7, comma, x not equal to 7. That's the answer form that I get. You can also take this negative and distribute it. On the top, it would look like negative x minus 7 over x minus 7. You can also distribute it on the bottom, and that would make minus x plus 7. Now rewriting it, 7 minus x, and we can switch these because they're both addition, 7 plus x. That's actually the answer in the back of the solution key. But either way, they're equivalent. So whichever one, the first one you get to, that is full credit. All right, let's take a look at what's next. Okay, new objective. Objective 4, multiply and simplify rational expressions. Okay, so we can reduce factors of 1. Now I see a factor of 1 here, this p and one of these p's. But these are separate terms, and so we want to factor them. So I'm going to factor out a 4, greatest common factor out of the first binomial, the p in the denominator. The numerator, I'm going to actually write the p squareds as separate p's so that I can reduce one nicely. Factor out the 8. Okay. And now with this 4 and the 8, I actually considering writing the 8 as 2 times 4 as well. So now everything's factored in such a way that we can see the reduction of the powers of the factors of 1. And what's left on the top is 7p And the denominator is just 2. All right, let's take a look at the next example. Example 2. All right, factoring. So the numerator, k and k, 4 and 2, both plus. That'll give us k squared plus 8, and 4k and 2k is 6k. Perfect mixture. Denominator, k plus 4 and k plus 4. K squared, 4 and 4 is 8k and 16. Numerator, this is greatest common factor. It's a simpler form of factoring. I always look for greatest common factors first. Denominator. Oh, now notice, I see this now. This entire 3-termed factor right there and this one, those would have just reduced. However, we're factoring them. I'm not going to factor it again. I know the answer. In general, the general technique is factor everything and then reduce. So let's see. That goes out. There's our answer. K divided by k plus 4. All right. Excellent. We're down to our 5th objective. Let's take a look at it. Divide and simplify. All right, so the division line. What we can do when we're dividing by a fraction is change it, and I'm not doing anything except for this step. Multiply by the reciprocal. Okay, now factor. Greatest common factor of 5. And the x, I'm going to rewrite this x cubed as x and x squared. And my x minus 3. There's a factor of 1, and there's a factor of 1, leaving us 5x squared. Excellent. So when you have a division sign, just invert and multiply. Next example. Example 2 has another division sign. So this first step, all I'm going to do, oops, it should be an x, is rewrite it with the invert and multiply instead of the divide. So notice the right fraction, we're doing the reciprocal of it. Now I want to, oh, look at that. That's nice. I want to see if I can pull the biggest factors of 1 out of here that I can. So 18, 6 and 3, 9 and 2. Now the 9 goes into 45, so I'm going to write that as 9 and 2. X, and let's see, since I thought about that as well, 9 and 5. Okay, x squared, x to the 6th. I'm going to write this as x to the 6th. Oops, wow. Come on. There we go. I didn't leave myself enough space. Y to the 7th and y to the 9th. That y to the 7th, I want this one down, y squared and y to the 7th. 45, 95, x to the 6th. And the 30s are gone. By factoring to get the biggest factors of 1 I can, it just speeds up the process just a little bit. You can also go all the way down to a prime factorization. And on this problem, it would take quite a bit of space to write it. 2x to the 6th in the numerator. 5y squared in the denominator. Okay, moving right along. If I wanted to write this in prime factorization, 18 is 2 times 9, which is 3 times 3, and 12 x's. I don't even know if I'm going to have enough space. Denominator is 30, which is 3 times 5. Sorry, it's 3 times 10, which is 2 and 5. And 9y's. Hear my kids in the background maybe. Times, and the 30, which again is 3 and 2 and 5, how I wrote it. And 7y's, oops, 1, 2, 3, 4, 5, 6, 7, and the denominator 45, which is 9 and 5. 9 is 3 and 3, 5, and 6 x's. So this is the full prime factorization. You could go to this extent so that you could then 2 reduces, 3 reduces, this 3 reduces, this 3 reduces, this 2 does not, this 5 reduces. So there's our 2 and our 5 in our answer. And then 1, 2, 3, 4, 5, 6. There goes all the x's left over. There's the 6 left over. And 1, 2, 3, 4, 5, 6, 7. And there's the 2 left over in the denominator, 2y's. So if you had to go all the way to the prime factorization, that's fine. I'm just demonstrating that if you can get the biggest factors of 1 you can, that speeds things up a little bit. Now let's look at the third example. Okay, again the division sign. So this first step, I'm just rewriting. Good. Make sure when you rewrite it that you take care of the division and the multiplication and that you've done the reciprocal. Now factor. Difference of squares. So x plus 5 and x minus 5. All of a sudden, not in drought. Can't even talk. 5. There we go. Maybe I need some coffee or something. The denominator. That'll be x minus 4 and x minus 4 times the numerator. It'll be x minus 4, x plus 3, and divide, take the 10 out, and x minus 5. So this is full factorization. This is the prime factorization, except for the 10. And now there's no x plus 5. There is an x minus 5. There's an x minus 4. And no x plus 3. So our final answer, we have an x plus 5 and an x plus 3 in the numerator, and we have a 10 which goes first and the x minus 4 in the denominator. Okay. All right, last objective of the first lesson. Multiply or divide rational expressions and list all restrictions on the domain. There's one example of this, and this is it. So the first thing I'm going to do, it's a little bit different. I'm going to factor all the denominators right now before I do this invert and multiply, because I want to collect all of the restrictions. In these problems, we will do a lot of reducing factors of 1, and if that factor reduces, it doesn't decrease the restrictions. So we want to get all the restrictions before we cancel out and lose all the evidence of the restriction. So let's see, this is x minus 5, x minus 1. This one is x and x plus 2. And this one is x minus 5, x minus 2. So 5. X cannot equal 5, 1. Just a single x, that would be 0, can't be 0. Negative 2. 5 again, positive 2. Lots of restrictions. Okay. Now, I can do the invert and multiply. And it's just this one that's going to switch. So this one, I might as well take a moment and also factor that x out. So that'll be x and x minus 3. Denominator's done. Times x minus 2 is factored. Sorry, x minus 1. And the x plus 2. And multiply. We're now inverting and multiplying. All this goes on top. Great. And denominator 5 and x. Okay, now notice we have a new denominator. 5 can't equal 0, but x also can't equal 0. That's already in there. Sometimes when you invert and multiply, you get an extra restriction. And also, sometimes when you invert and multiply, another restriction that was in the denominator is in the numerator, and it doesn't look like a problem, like this x equals 2. Nothing in the denominator has a x equals 2 problem, and yet, originally it did. So that's why at the beginning, you want to grab all the restrictions, and then after you invert and multiply, grab any additional restrictions. And we have them all. So, now we reduce factors of 1. This x reduces, x minus 3 does not, the x minus 1 reduces, the x minus 5 reduces, and the x minus 2 does not. So our final answer, we have x minus 3 on top, the x minus 2, in the denominator we have 5x, and the x plus 2, comma, and all of our restrictions. Double check, that looks perfect. All right, that completes lesson 1.